Skyhooks are an ingenious device for fishing planetary atmospheres and catching spaceships. Today we are going to look at skyhooks, a type of tether system used in orbit to help get ships up into space with a lot less fuel. We are going to look at several different varieties, explain how they each work, how ready the technology is for deployment, and look at the cost and safety issues of this method. We will also discuss their uses far from Earth, everywhere from low-gravity airless moons to deep-gravity gas giants. We'll be at this for a while today, so you might want to grab a drink and a snack. Also, a quick note before we begin while you're doing that. We have looked at skyhooks before. It was one of the oldest episodes I did, and during a short phase where I took some well-meant but bad advice to keep the videos brief. As a result, the original Skyhook episode holds the channel's record for the shortest episode to date. That episode has always nagged at me because this topic, skyhooks, is one of the most useful and clever concepts out there for getting into space, as we will see today. I think when we're done today you'll be wondering why they don't get more coverage in science or science fiction, something that has puzzled me for years, because they are incredibly useful. Okay, introduction complete, explanation complete, drink and snacks acquired, let's dig in. Skyhooks come in a variety of forms and we will cover all of them, but the simplest one to explain, and thus for us to cover first, is the non-rotating kind. This is a lot like the space elevator we covered previously, only instead of running from the ground all the way up past geostationary orbit, the basic skyhook just runs from the upper atmosphere to lower Earth orbit or even higher. How far up depends on how strong your material is. Like space elevators, you would ideally use carbon nanotubes and taper the tether to be wider at the top than the bottom, to get the tether as long as you can without it snapping under its own weight. Let's consider the motion of this tether. Unlike the space elevator, it is not holding a fixed position over the ground. It is orbiting, but the orbit is a bit weird. You see, how far away an object is from Earth controls its orbital speed, at least for totally circular orbits, which is what we're contemplating at the moment. The higher up you are, the slower the necessary orbital speed to avoid falling down. Just above the atmosphere, things orbit about once every 90 minutes, or 1.5 hours, at a speed of about 7.8 kilometers a second. If we went up about 4,000 kilometers higher, things orbit about once every 3 hours, taking twice as long, and moving at about 6.1 kilometers per second. A difference of 1,700 meters per second, and a big difference, since that speed would get you from the west to east coast of America in under an hour. Again, the higher object is moving much slower and takes double the time to orbit. Now let's say I took a super long and strong tether and connected those two orbiting bodies. What happens? They have to move together now, but their orbital speeds are a lot different. To be in a stable orbit now, they would need a period somewhere in between the 90 minutes and 3 hours each previously had. Because gravity is not uniform, we can't assume it would be right in the middle at the center of mass. Also, because the tether is wider near the top to make it stronger, more of the weight is nearer the top. So we will say now that the whole thing wants to orbit every 2.5 hours. And that is what it will do. But that means the top and bottom both are also doing so. So now the top is not moving 6.1 kilometers per second anymore. It is moving 6.8 kilometers per second instead, a lot faster. Down at the bottom tip, the reverse applies. Before it moved 7.8 kilometers per second, but now it isn't orbiting every 90 minutes, but every 150. It is only moving 4.7 kilometers per second, about 60% of its original speed. If a rocket or shuttle could get itself up to 4.7 kilometers per second, instead of the normal 7.8 needed for orbit at low altitudes, it could get hooked by that tether, climb up it, and exit anywhere along the way, having transferred momentum from the tether, the skyhook, and enter a normal orbit anywhere along the way or even higher, since the top of the skyhook is moving faster than is necessary to orbit at that height. A longer and stronger skyhook could match up at an even lower speed at the bottom tip and even higher one at the top. Sounds good, but how good is 60% slower for orbit? doesn't really seem that much of a game changer for spaceflight. But consider, your typical liquid hydrogen and oxygen rocket has an exhaust velocity of 4.4 kilometers per second, just a bit less than the 4.7 our bottom tip, the hook, is doing. To get up to normal orbital velocities, that rocket would need to be about 83% fuel under ideal conditions, 5 kilograms of fuel for every 1 kilogram of payload and ship. To get up to 4.7 kilometers per second, it only needs to be 2 kilograms of fuel for every kilogram of ship and payload, just 40% of the fuel. And that was without including the equatorial spin launch bonus that both rockets would receive, but which benefits the slower rocket even more proportionally, or the extra drag higher speeds impose. What's more, for those lower speeds, we have a lot more options available to help something get to that speed without rockets, though we will contemplate hybrid systems like shooting our shuttle down a massive railgun later in the series. But you can see the benefit. That is a lot of fuel saved. A longer cable can do even better, but we've already massively cut down on the fuel per launch. It still isn't ideal though. I mean, 4.7 kilometers a second is still insanely fast. That's Mach 14, more than double the record for jets. Also, you are probably wondering what happens to the Skyhook. If it is giving the spaceship it hooks a lot of its momentum, why doesn't it fall down? The answer is that left to itself, it would, making the Skyhook essentially a disposable device and thus less beneficial since you need to spend fuel getting it up there and more to put it back into place after each lift if you want to reuse it. Otherwise, after a few uses, it will sink into the atmosphere and burn up. There are ways to regenerate that momentum for reuse without using tons of rocket fuel, though we will discuss those later. Let us consider a couple alternatives to our basic Skyhook, one that just hangs over the ground doing a slow circular orbit, probably over the equator to maximize the equatorial spin bonus, but it can orbit at any angle, and you can arrange to have it go over any specific spot on the ground at regular intervals. The first to consider is another identical tether hanging higher up over the first one. It has the same basic dynamic. The bottom is moving slower than it should, and the top faster. So you could arrange for your ship on the lower tether to jump over to the higher one and gain more speed, which is very handy, especially since you can make the tether longer the further they are from the Earth and its gravity yanking on the tether to rip it apart. This also means that you can always use a ladder of these tethers with any material, just one after the other, even if your materials only let you make a tether 100 kilometers long, and we can do way better than that with existing materials we can already mass produce. But the problem is, it doesn't help with that initial hook, which is the important part. Such a ladder is great for getting higher up without more fuel, but doesn't help much getting into orbit in the first place. We want the bottom tip of that hook to be going as slow as possible relative to the ground. So we have a solution. We spin the tether so it cartwheels in space around the planet. If our previous tether was 4,000 kilometers long and naturally gave us 4.7 kilometers per second at the tip, if we spun it backwards when the tip dropped to the bottom of its spin, it would be going slower than that. Let's assume it's spun around 3 times every orbit, which was every 2.5 hours or 150 minutes. So it spins once every 50 minutes. Now that tip is drawing a circle with a diameter of 4,000 kilometers, or a circumference of that times pi, 12,600 kilometers, once every 50 minutes for a speed of 4.2 kilometers per second. Well, the tether was already down to 4.7, so as it swings backwards into our upper atmosphere, that tether tip at the bottom of its course is just 500 meters per second. That's pretty fast, but it's only Mach 1.5. Faster than most commercial jets, but slower than the Concorde used to cruise at, and way slower than the top speed we can make an air-breathing jet fly. In fact, since the equator is spinning at just under 500 meters per second itself, on the equator, this hook would spin down there at the speed of a normal car, and a hook just a tad longer could actually snatch a stationary object. Pretty handy, on paper anyway. This degree of performance is a bit trickier to achieve than it sounds like. For one thing, you have air drag to worry about, but on an airless or nearly airless place like Mars or the Moon, where you can also have longer tethers from the weaker gravity, this rotating method can be combined with a slightly elliptical orbit to have the tether dip down and snatch something right off the ground and swing it up into orbit. Also, this rotating skyhook, commonly known as a rotovator, is spinning forwards at the top of its spin in the direction of the orbit. meaning it can launch whatever it grabbed from the surface into high orbit at tremendous speeds. With ideal materials such a rotating skyhook, a rotovator, could pick a man right out the ground on Mars and chuck him straight back to Earth. I doubt he'd survive that trip, but it would work with cargo containers or spaceships on the landing pad just fine. But it has some problems, especially if you have air, since that hook would experience a lot of drag swinging down through the air. The other problem though is the tether. Doing a 4,000 km long tether is already kind of pushing it if we're not using perfectly manufactured carbon nanotubes and tapering the tether. But that tapering is designed to make something wider at the top than the bottom and thus stronger, as we discussed in the Space Elevators episode. That goes a bit out the window when the thing is spinning, so that the top isn't always the top or the bottom. We can still benefit from that partially, but mostly by allowing the weight of the ship to be included on the bottom when the bottom is actually down near the planet. It doesn't really let you make a vastly longer tether than an untapered one. That's okay, we use a shorter tether but we spin it faster, right? Well, no, because when you start spinning something around, it has centrifugal force trying to rip it apart. A tether spinning around far from any gravity well can still only spin so fast. Same as when we discuss rotating habitats producing spin gravity, we can only make them so wide or they'd tear themselves apart. So our rotating tether, our rotovator, cannot be as long as our non-rotating tether because we can't take as much advantage of tapering it, and we can't make up too much of that loss by spinning it faster because it will tear apart. At the bottom of that hook, when it is spun down near Earth, it has all of Earth's gravity yanking on it, plus the centrifugal forces pulling that tether down the same direction, adding to the force. The rotovator design still has a lot of net advantages, especially when you've got much stronger materials or are working in a weaker gravity well, but it isn't too likely to let us snatch regular planes out of the sky. But it should be able to grab some hypersonic spaceplane designs that have been proposed, and we'll talk about those later too. We still have a couple more types using more clever tricks, but I'm going to skim past the cardio rotovator design. Same basic concept as the rotovator, another long tapered tether that rotates, but does so on an elliptical orbit, rotating twice every orbit. The trajectory of the tip is roughly heart-shaped, so we call it a cardio rotovator. It has a few minor advantages over the normal rotovator, and a few disadvantages too, but it is essentially taking advantage of how elliptical orbits don't have the same speed all the time. In a circular orbit, an object stays at the same speed. In an elliptical one, they are fastest when they are closest to the object they orbit, called perigee when that object is Earth, and slowest when furthest away, called apogee for Earth. If we use a long tether that can reach down from apogee, it will be going slower there than normal, and so the rotating tip will also be going slower. Because of this, it has to do exactly 2 spins for every orbit, so that the long tether doesn't smack the planet when it is at perigee. The system isn't as flexible, but still slightly outperforms the basic rotovator in some key ways. The last variation I want to discuss quickly is called the T4 or Tillotson 2-tier tether. This is a spinning tether with another spinning tether on the end of it, called the first and second stage respectively. As mentioned, one of the issues with spinning a tether is the centrifugal force trying to rip it apart, and that rises linearly with how long it is, and with the square of how fast it is spinning, its angular velocity. So the longer it is, or the faster we spin it, the more force acting to shred our tether. But if we use a shorter or slower spinning tether with another tether on the end spinning too, the dynamics change a bit. You arrange the rotation so both are sweeping backwards when it goes to hook. Same basic concept, but this system lets you use a shorter tether under higher acceleration. I've noticed both the cardio rotovator and T4 can confuse folks a little, and they don't really alter the basic dynamics of the concept much, which is part of why I skipped them entirely in the first Skyhook episode. But I did want to give them a quick mention this time, and I should note there are some other variations on this concept. I'll attach some links in the video description for any of you who want to explore those and who feel more comfortable with the math and orbital dynamics. Now, I mentioned earlier that one of the problems with a skyhook is that once you hook something and begin lifting it up, Newton says the skyhook has to go down. It is sharing its momentum with the thing it is lifting up. So if you don't do something to regenerate that momentum, your skyhook will have a limited number of uses before it falls down into the atmosphere. goodbye Skyhook. Even disposable hooks have some advantages, but we want to keep ours for many uses. But if you want to do that, you have to restore its momentum after each lift. Now the obvious way to do that is with a rocket, but that somewhat defeats the point of having these things to assist rocket launches. However, we do have some better options. First, there are drives you can use in space that are too weak for launching, but much more efficient overall, like the ion drive. We discussed ion drives at greater length in the Spaceship Proportion Compendium, but in short form, ion drives, especially if they can get external power from solar panels, can use a tiny amount of propellant to achieve much higher final velocities than rocket fuel allows. Unfortunately, they do this very slowly, so are totally useless for getting into space. However, a Skyhook with solar panels on it to power an ion drive can use that to slowly restore momentum between hooks, and you just need to make sure ships getting hooked occasionally bring up some propellant. Preferably xenon, but many other more abundant fuels like argon do the job almost as well, and it is less important which you use for an essentially stationary tether as opposed to a spaceship going to Mars. You can refuel as needed, so you just use whatever works well and is easy to get, especially if you don't need to get it from the Earth. And you can also source those from places other than the Earth. There's nothing particularly complex about getting argon from the moon, for instance, thus avoiding Earth's gravity well entirely, and Skyhooks work quite well on the moon too, no air drag. More on that in a minute, but it's worth noting that the propellant wouldn't have to come from Earth. Solar panels ionize that propellant and slam it out the drive, restoring momentum to the hook without needing to bring rocket fuel up from Earth. Now we don't actually need propellant here on Earth. The handy thing about Earth is that it has a giant magnetic field, probably the major reason we have a breathable atmosphere. The nice thing about a giant magnetic field is that if you have a long tether of some conductive substance inside one, you have a large electrical potential between the top and bottom of that tether. This allows you to use Lorentz force to push on our tether. By applying electricity, presumably from solar panels, we can basically push off the planet's magnetosphere to restore momentum, using a trick known as Electrodynamic Tethering. This is also potentially handy for station keeping of satellites, but one has to weigh the ups and downs of including some mass for a tether versus some fuel for a rocket, and tethers are also a bit of a navigational hazard, especially if you're using tons of them. Since we already have a tether anyway, waste not, want not. You can also use this trick backwards to generate power by removing momentum, but we'll skip that for today. Now, electrodynamic tethering would certainly seem preferable to ion drives, no fuel or propellant at all, but as I mentioned, Skyhooks can be used in more places than just Earth, and not all of those would have a nice big magnetic field to use. By the way, while we are speaking of magnets, I should probably mention that the hook itself, the thing that grabs the payload down at the bottom tip, doesn't have to be anything mechanical. A nice big electromagnet that can slam onto the metal frame of whatever you're hooking minimizes some of the problems matching up speeds. If you've ever seen a mid-air refueling, you can kind of guess that this is not exactly a simple operation, especially when everything is moving supersonic. But we have the option for electrodynamic tethering or ion drives or some others for regenerating momentum. Which of those you do might depend on where you are doing it. On an airless rock like our moon, a Skyhook could flat out swing down to just over the ground and grab something. The Rotovator version, using conventional materials, could pick stuff right off the ground because there's no air drag. Of course, our moon, and most airless places, do not have very strong magnetic fields, so odds are good you'd want to go the ion thruster route instead. But Skyhooks would work great for the moon, though since we already have materials strong enough for building a space elevator there, it might seem a bit redundant. But remember that a Skyhook doesn't just pick you off the ground. The rotating kind accelerates you very quickly and fling you away at high speeds, and do not require as long a tether length compared to a space elevator. Mars would be an ideal case since it has very little air, but still has strong enough gravity to make a space elevator a dubious proposition. Skyhooks are also handy for deorbiting on airless planets too, where we have no drag to help us slow down, since we can arrange for them to lower a ship's speed as easily as increase it. They also have applications in places where a space elevator is unlikely to ever be practical, like a gas giant. Those typically have huge magnetospheres to help recover momentum, and they also have huge amounts of gravity that would snap an elevator. plus no ground or sea to tether anything to at the bottom. Bases on gas giants either need to be super light to float in the low-density hydrogen and helium gas those are made of, or constantly flying to generate lift. Also a topic for another time, but skyhooks might be advantageous there too, or even for walking near the sun, and we used some similar tricks to electrodynamic tethering when we discussed harvesting material from the sun in the star lifting episode. Of course, one of the problems with tethers is they can only be so long before they'd break, same as a space elevator. These things rely on tensile strength. As I mentioned earlier, we could essentially build a ladder out of multiple skyhooks, rotating or non-rotating. Transferring between them is a bit of an exercise in good timing, but nothing even the simplest modern computer couldn't handle. Your ladder, composed of rotating or non-rotating hooks, or a combination of both, can include as many components as you like, and each one as long as the material will comfortably permit based on its strength, the gravity at that distance, and the centrifugal force it experiences if spinning. This sort of skyhook ladder, combined with electrodynamic tether momentum regeneration, ensures that you can get off any planet relatively cheaply, even ones more massive than Earth. And even if you never figure out how to mass manufacture super strong materials like graphene, as good old Xylon or Kevlar will do the trick. And you can have multiple hooks in the same orbit, even at different orbital angles, to ensure that you can do a lot of pickups and cut down on time delays of waiting for higher hooks to come back around for a transfer. However, these are long cables, and even the non-rotating ones are a bit of a hazard, so you don't want to clutter space up with too many of them without doing some very careful coordination of orbits. This does raise safety issues though. Skyhooks are also probably the safest of the launch systems we will look at in this series. They move around the planet quite quickly, so if they drop into the atmosphere, they just burn up. As with the space elevator, we have the option to include the occasional explosive charge to break the hook into smaller bits. It shouldn't really be necessary to do so, but something I forgot to mention in the space elevator episode is that the proper spacing and timing of explosives on tethers, skyhooks or space elevators, can help you control where they drop, which is handy since most of the planet is ocean, and even most of the land is sparsely populated. Better the ocean than land, but better a wheat field in Kansas than New York City. Again though, these will reliably burn up in the atmosphere, so there's little need to worry, nor would they do much damage if they hit. The big safety issue is the hook and the plane not matching up, or it snapping when the hook was made, but that is one of the reasons why a plane carrying a payload is preferable. A plane can more safely and easily maneuver to an airport to land, so if you miss a hook, the plane just diverts to an airport or loops around to return to its launch site. They are a bit of a hazard to space navigation, and also vulnerable to space debris hanging around orbit, but not too much of one for the former, and we'll talk about the latter soon, but not today. Overall, skyhooks are quite safe, safer than rockets I suspect, particularly once they've had as much service time for us to learn their quirks and hazards as we have with rockets. But even more than safety, the nice thing about skyhooks is that they are cheap. They don't offer the same super low launch costs as Space Elevator does, but they come close and are way cheaper to deploy. This is a technology we already have and which wouldn't need a lot of prototyping. It is just an immense chord, and though the momentum regeneration angle is a bit trickier, that is also on very solid and old scientific footing. R&D is needed, but more in the way a new car design needs it, as opposed to trying to build a hover car or something. Also, while neither Kevlar or Xylon are cheap compared to steel, they are in the dollars per kilogram range. So if we imagined a cable of it 2,000 kilometers long, massing say 100 grams a meter, or 100 kilograms a kilometer, that cable would only mass 20,000 kilograms, which is on the heavy end of a normal single launch, but quite doable, and would only cost you a couple $100,000 to manufacture, though presumably several $100 million to launch. Since they would instantly save you a big chunk on launch costs of every future flight, it pays for itself after just a handful of launches. If you were pretty confident that your electrodynamic tethering would work first try, you could even use the hook to snatch up all the solar panels and equipment needed for regenerating the hook's momentum on your second launch. So unlike the space elevator and most of the other systems we will look at, it does not have the huge initial capital investments of R&D, prototyping, and construction. It does not offer you quite the same super low cost per kilogram launched some of the other options have, or the ability to move truly huge amounts of cargo back and forth to space. Nor can you use these right next to your big cities, sonic booms and all, but it is a strong candidate for near-term use, safe, cheap, and relatively low tech. In fact, your biggest R&D cost would probably be those hypersonic planes meant to connect to the hook, though there are some alternatives we will discuss for getting spaceships up to the necessary hooking speeds besides hypersonic jets. Back at the turn of the century, when we were thinking about replacing our space shuttles with spaceplanes, Boeing worked out a system using skyhooks called HASTOL, the Hypersonic Airplane Space Tether Orbital Launch System, in a partnership with Tethers Unlimited. It used a hypersonic airplane to get up to the highest speed an air-breathing jet could pull off, then link to a spinning tether, typically releasing a payload to attach to the tether since the plane is then useless mass, which can then land elsewhere, refuel and reload and do it again. The idea didn't go much past the drawing board, but not because the tech wasn't promising or was too blue sky. We never did replace the space shuttles with spaceplanes, as was the general assumption we would do at the time, and this was one of the stronger candidates. You don't necessarily need to use hypersonic planes either. It can be adapted to work with conventional rockets, it's just that planes would tend to be cheaper once you got done with the R&D. I'm not sure which companies are looking at Skyhooks right now. A lot of folks are mostly focused on reusable rockets at the moment, and that is a very promising technology we'll be looking at soon too. Also, again, you can adapt Skyhooks to work with those too, so I think as the technology progresses, Skyhooks will get a second look for possible use with them. If not, they will likely make an appearance to work in tandem with some of the other systems we will discuss in future episodes. They are very much a launch assist option, meant to be used as a hybrid with something else that helps them get up to the necessary hooking speed. I think we will stop there for today. Hopefully by now you see why I felt the system deserved longer coverage than I gave it in the original episode, and it remains my personal favorite in terms of near-term technology to make space cheaper. As we've seen, the Skyhook is cheap to construct and launch, the main cost being related to the development and production of a fleet of hypersonic airplanes. While the launch cost reductions are not on par with, say, the space elevator or the orbital ring, it still offers considerable reductions in launch costs. We will look at the orbital ring later in the series. Next week though, we will take a look at life support, and look not at ways of getting into space, but ways of staying alive in space. And we will look at a lot of the options available and try to give some solidity to them. After that, we will return to this series to look at mass drivers and similar concepts for getting into space, or at least up to high speeds, by accelerating a ship down a long tunnel like a cannon shot. For alerts when those and other episodes come out, make sure to subscribe to the channel. If you enjoyed this episode, please like it and share it with others. Until next time, thanks for watching and have a great week.
Thank you.